All right, so today we're going to continue talking about routing, but we're going to focus more on the issues related to vehicle routing. Then we're going to look at some traveling salesperson heuristics, and this will be specifically for vehicle routing. And finally, we will look at the sweep heuristic, which is a flexible heuristic that is used for vehicle routing for the special cases where you have multiple vehicles. So in terms of vehicle routing, it can be used in all kinds of contexts, passenger transportation, service operations, where you don't have a delivery of any particular product, but you have the execution of some service, and of course in our case freight transportation. So routing is used in a number of different arenas. In terms of classification, it's pretty obvious. It's self-explanatory, all the different ways in which you can classify the different vehicle routing problems, and a lot of these can be solved as mixed integer linear programs. You can have multiple classifications. So for example, you can have known demand and a directed network with a limited route time. So you can have multiple objectives if you want to call it that. Minimizing costs, minimizing miles, number of trucks. Again, it depends upon how you construct the problem. Like I said, this is just a laundry list of the different objectives and classifications. All of them are pretty self-explanatory at this point. One of the things I will notice, I will point out, is the balancing of the workload, and we will talk about a way in which we will solve a balancing workload problem using an integer linear program, not a mixed integer linear program, but that will be towards the end of the class. Now, one of the things about vehicle routing is it becomes very complex because there's a whole bunch of different considerations, both from the shipper's perspective, the customer's perspective, as well as the vehicle operator's perspective, whether it's a truck or it's a rail car or if it's a barge of some sort. So there's a number of different perspectives that come into that. Clearly, time windows, we will see, make it complicated. And then, a number of different operational characteristics. And, here's another laundry list of these considerations, which are pretty much self-explanatory. So, at this point, those of you at least who are taking transportation should have come across all of these characteristics. So I'm not going to belabor the obvious. So let's talk about the traveling salesperson's problem, but from a vehicle routing perspective. Again, we were concerned with visiting a set of nodes, but this time we don't have a single salesperson, but we have multiple vehicles. So that's the key difference between the TSP and a VRP, is that you have multiple vehicles in a VRP problem or vehicle routing problem. And also with a VRP, you have the issues that we just glossed over very quickly: time windows, sequencing, contractual issues, load compatibility, etc. So when you have so many considerations to take into account, and when you have such a complex problem, typically you want to follow some very simple principles in order to start and solve these problems. So the first one is you should typically try to serve all customers in the same geographic area on the same day. So when you take a look at an example, you say you have on the right-hand side, for example, let's take all of these customers that we want to serve on a Thursday. And so this is what our route should look like on Thursday. And all of these customers we want to serve on a Friday. And this is an acceptable way of routing. But we can improve upon this by clustering it even more tightly according to the geography by saying all of these customers that are close together we serve on Thursday, and all of these customers that are close together on the right side we serve on a Friday. Now, implied in this is clearly something that we can see is obvious is you want to cluster these stops so that they are geographically close together. So the way you'd want to do that is, depending upon, again, the clustering that you want to use, you could use, say, a east-west clustering, and you could say, let's cluster these stops together and these stops together. So this would be our route. Or we could do more of a north and a south type of clustering. So all of our customers in the north part of the region, we serve with one vehicle, and all of the customers in the south part of the region, we serve with another vehicle. So one route is typically one vehicle, and so you see that you have one vehicle that serves customers in one geographical region, and it's pretty intuitive to see why, because now you're not wasting miles and fuel and driver time going from one region to another. All of your stops are pretty close together. You complete all the stops and then you return to your depot. And then finally, you'll see that what we've been trying to follow all along is, as we've been drawing our routes by eye, we've been trying to form more of a teardrop pattern where the apex of the teardrop is at the depot. So you're starting at the depot, you're going out in a round, and you're coming back to the depot. Okay? And you don't have any crossovers. As we saw, when you have a crossover, you're adding distance to your route. So that is typically taken care of if you follow a nice, clean teardrop pattern. Some of the other practical principles, you want to fill up your largest vehicle first. So why would you want to do that? Why would you want to fill your largest vehicle first? So if you have a range of vehicles, different sizes, and you have multiple customers to serve, and you start with your smallest vehicle, then you're going to quickly run through all of your small vehicles until you have the largest vehicle, and you might not have enough to fill up your largest vehicle. But if you, on the other hand, fill up your largest vehicle first, then you make sure that that largest vehicle serves as many customers as possible, and then your smallest vehicle, which uses up less gas mileage, might either be full or might be half full, but it doesn't really matter because you're using a lot less mileage in that smaller vehicle. You typically want to do pickup and delivery together, so you want to mix customers that have pickups and customers that have deliveries in the same route. And if you have one customer that's far away from your typical geographical region, then you might either want to outsource that, or you want to probably have a dedicated small vehicle that is used solely for that one customer. And finally, for time windows, you want to make sure that you avoid narrow time windows, because with narrow time windows, what happens is it becomes a lot harder to do things like sequencing your delivery and pickups in the same route. It becomes harder to do all of your pickup and deliveries with one truck. You might have to have multiple vehicles. So it becomes a lot harder and more expensive when you have tighter time windows. So, you have typically a set of procedures where you want to follow when you're doing routing and scheduling. The first thing that you want to do is you want to calculate the distance between the stops, and you can do that in a number of different ways. On a homework or an exam, you can use the Dijkstra's algorithm, right? You fix one stop as the origin, and you can calculate the distance to the other stop. So you calculate the distances between the stops, and then you try to determine how you can segment the different stops and assign it to different vehicles. And then for each cluster of stops, you want to route the vehicle in that cluster of stops in the optimal way possible. And then you find all of your routes, and you see if you can combine smaller routes and break up larger routes so that you balance the work schedule for your drivers. You typically want to give all of your drivers a similar type of 9 to 10 to 11 hour day maximum driving, or 12, 13, 14 hour day on duty, so that all of your drivers are paid about the same. So that's why you want to be able to make those final adjustments. So according to those steps, we either route first or partition first and partition later or route later. So we look at a couple of these to start off with, and then we look at how we can do them simultaneously with the sweep method, the savings method. So the route first, partition later is the TSP method, and you find the optimum route using any of the TSP heuristics that we just discussed in the last lecture, lecture 11.1. So I think it was lecture 10.1. So in the TSP methods, you could use the Christofides algorithm, you could use the nearest neighbor, and you could find the optimum route. Then you go on to the route, and then you partition the route into the segments according to how long you have to execute each segment of that particular route. And then you determine how many vehicles you need to fill up the route. So I'm not going to show you a demonstration of this, but the link is provided to you on eCampus. Go on to eCampus and look at the demonstration and see how that is done. Basically, you come up with the route, and then you see how the route is segmented into the different partitions, and then you determine the number of customers that you have, or the number of vehicles you need in order to serve those different customers to satisfy all of the pickup, all the deliveries for your group of customers. The next method is a sweep method, and that link also has a demonstration for the sweep method. Here we first partition, and then we route within each partition. So the first step is where we assign the different stops, and then we determine how we are going to route, or the stop sequences are determined within each cluster or partition. So let's look at the sweep method. So these are the steps that I'm going to demonstrate in our example. Um, and by the end of it, we should have our the number of vehicles that we need to complete all of the deliveries or the pickups, and we also will have the optimum routes for making all of those deliveries. So right here at the center we have warehouse, and we have the customers in dots with the demand for each customer, and the vehicle has to start at the warehouse and make the deliveries to the customers, and we have to find out how many vehicles and which customers assigned to which vehicles, and how do we route or sequence the customers within each partition. So the first thing to do is to draw a ray from the origin in any direction. So I'm just going to pick a north-south ray, and I draw it vertically upwards. Okay, and now we can rotate the ray either to the left or to the right. I'm going to rotate it to the right, and the capacity of the truck is 20. So I want to make sure that I hit 20 before I fill up a truck that says that there's one truck that is going to be able to satisfy those customers, and that's where I end my partition. So I'm going to start with 2. So I'm basically taking this ray and I'm just rotating it to the right. So and as I hit a stop, I add the number of items to deliver. So there's 6, 9, 14, 17, and 20. So I've hit my capacity right there. So this is my first partition. And now I'm going to start my second partition. So I'm going to continue my sweep. 1, 3, 7, 10, 15. And notice that when I hit 6, 15 plus 6 is 21, which puts me over. So I don't add 6 to my partition. I end my partition right there. So now that becomes my second partition. And this way I continue to partition. So now I have 6 plus 3, 9, 13, 15, and 20. So now I filled up a third vehicle. That's my partition of customers for the third vehicle. So I go 4, 9, 13, 16, and 20. So I have 20 over there, and then finally I have 2, 5, and 7. So 4, and then finally I have 5. So I have 5 trucks, and now I go in and route. I use the simple principle of drawing a teardrop shape. So starting with the depot as my apex, I just go out and I hit all of my stops as best as I can. So after partitioning all my stops, now I route using the simple principle of drawing a teardrop shaped route, and I'm able to now find my routes as close to optimal as possible. So that's the solution to the sweep for this particular problem. So there's an example here which you can try on your own. This time the trucks are limited to 6 stops each. So now you just have to count the stops instead of counting the amount of deliveries or the pickups at each stop. So remember, draw ray in any direction. Yes, Ray.
In the fifth partition, did we miss a 2 up in the top left corner when you drew the route?
Well, I blanked this out and I put the dot up here.
Move to the left, the little down.
Yeah, this is supposed to be a blank. So I put a white piece over that, but for some reason it did show up a little bit. But there was a circle here which I went through. Yeah. So when you route, or when you partition rather, you find that you have 7 different vehicles that you need to employ, and then once you partition it, then it's a simple matter of just sequencing the routes within each partition. And you have to remember that you can draw the first ray. I drew my first ray in this direction. You can draw a ray in any direction. And again, I went clockwise, but you can just as easily go counterclockwise. So the solution could be quite different depending upon the ray direction and the direction in which you rotate the ray. Michael?
So I thought it's only 6 stops.
Yeah.
So why does the, if you go clockwise, why does the second one have 7? Next one.
Which one?
The one next to that.
I couldn't count.
Make sure.
So probably I should have excluded this sixth one here, drawn the ray. So all right, so when you evaluate the sweep method, you can see it's very easy to learn. And in a computer program, which you're typically going to see the implementation, you can run very quickly. The problem is you cannot include time windows very easily in this method. Another important characteristic of this problem is because you can draw the ray in any direction to start off with, and then you can rotate the ray either clockwise or counterclockwise, you can come up with all the possible solutions, which basically is if you have n number of points, you can draw the ray next to any one of those n points. Okay? And then since you can rotate it either left or right, you can come up with twice the number of points. The solution has twice the number of points, 2n possible solutions. So in a computer, you can run and find the shortest and the minimum number of trucks or you can find all 2n solutions and then pick the best one according to whatever your objective is, either minimizing time, maximizing customer service, miles, fuel burn, whatever your objective is. So in general, research has shown that this method is about 10% from the optimal, which is not bad because you can get an answer very, very quickly. When you compare the sweep method versus the TSP, and when you go onto the link that I put for you on eCampus, I urge you to look at these conditions and to see how the TSP and the sweep perform against each other. You'll see that in general, the route first partition works better when you have sites that are evenly dispersed. Okay, there are no clusters of these sites or the customer locations. Also, the truck capacity is relatively small compared to the total customer demand. On the other hand, when you have concentrations of sites around the depot and when you have a large truck capacity compared to total demand, then the sweep method works better. Okay, so let's look at the Clark-Wright savings method. And then we will look at a binary program, an integer program for sequencing the routes, for balancing the workloads. So when you look at the Clark-Wright savings method, it's where we partition and we route simultaneously. So we start off with an out in the back solution, which is the most expensive solution. Okay, it's the greatest cost solution. And the out in the back solution basically is from your depot, you select one vehicle that goes to every single customer, goes out to the customer and comes back. So if you have 3 customers, A, B, and C, you have one vehicle that goes to A, one vehicle that goes to B, and one vehicle that goes to C. Okay, so this is your most expensive solution. You have 3 vehicles, each one just visit one customer. So that's your out and back solution. That's your most expensive, and that's where you start. So the savings comes from the fact that I'm going to now combine these methods. So I'm just going to redraw it. You don't have to redraw it. So from the depot to, let me color code these. So from the depot, let's call my subscript I customer A. I make a savings by removing that particular arrow. Okay? So I remove this arrow, the depot to customer A. I also make a savings by removing one of the arrows going from depot to customer J and let that subscript be the customer B in our case. So now I'm going to take out this arrow. So I'm saving those distances. So what's happening is I'm actually adding a new distance or a new route from A directly to B. Okay? So these are savings I'm making. So that's I'm adding those savings. And because I'm adding this additional route, now I have to subtract that additional distance from my savings. Okay? So my total savings, the heuristic is going to maximize my total savings in a way, to combine routes in a way that will maximize my total savings. Okay? So that's how the heuristic works. So what I'm going to do in heuristics, I'm going to keep repeating and finding out ways in which I can combine stops and combine stops into existing routes. So I can, that's another important feature of the Clark-Wright savings method, is if I have a route, I can combine another route, I can combine another stop into that route to realize more savings. And I'm going to keep doing that until I stop, until I have all of my routes. And if I violate some of my time windows, then I'm going to have to stop. And that's the solution to my Clark-Wright savings method. So the good thing about the Clark-Wright savings method, just as I've alluded to, is you can have constraints such as, of course, truck size, which we had with the sweep and the TSP as well. But you can also have time windows where you can limit the number of stops based upon the time windows that are specified by the customers for delivery or pickup. So let's look at an example here. So we have 5 customers here, and the time windows are given to them, are given adjacent to them. And we have to start our deliveries 8 o'clock in the morning from our depot. Now, we have a grid system over here, and each square is 1 mile, and it takes 15 minutes to complete that 1 mile. Okay? So the first thing that we're going to do is we're going to do what? What is the first step in the Clark-Wright savings method? Is we're going to assume that we have 1 truck for every stop, right? So we draw the out and the back solution. So now we have to look at stops that can combine, that we can combine to realize the greatest savings. So what stops can we combine to realize the greatest savings? Clearly A and B, right? Oops. So what happens when we combine A and B? So when we count the number of the squares, we can see that this is 9 miles, this is 2 miles, and this is 9.2 using simple Pythagorean math. So our savings from combining A and B, oops, will give savings of 9 plus 9.2 minus 2, or 16.2 miles. So what about the time windows? So we start from the depot and we go first to A. Remember, it takes 15 minutes per mile. So this is going to take us 2 hours and 15 minutes. So from 8, 2 hours and 15 minutes puts us at A at 10:15. Then we wait till noon. At noon, it takes 30 minutes to unload. That takes us to 12:30. 2 miles takes us half an hour. So we reach here at 1 o'clock. We finish unloading. 1:30, we're within the time windows, we can get back. Okay? So we won't violate the time windows. So combining A and B is going to give us a savings of 16.2 miles, and we won't violate the time windows. Okay? So what other stops can we combine? C and D, all right? So we count the number of steps here. This is a number of squares. We get 10 miles over here. Then C to D, that is 6 miles. And by Pythagorean math, we know that this is 11.7 miles. Okay? So, combining C and D would give the next most savings, where S is equal to 10 plus 11.7 minus 6, which is equal to 15.7 miles. How about the time windows? So we start here at 8 o'clock in the morning, and it's roughly 12 miles. So it takes us about just shy of 3 hours, say 2 hours 50 minutes. So 2 hours 50 minutes we take to get here. We get here at 10:50. We finish unloading. Once we get here, we finish unloading at 11:20, half an hour later. 6 miles takes us 1.5 hours. So we are there 11:50. So we finish unloading at 11:20, 11:50, 1:50, and that's after, 12:50. That's after the 12:30 time window when we get to C. And you'll see when you try to come to C first, so that's 2.5 hours. We'll be here at 10:30. We have to wait till 11. And 11, we finish 11:30. We're not going to get there before 12, okay, because it's 1.5 hours. So we're not going to make the time windows. And as a result, even though we realize some savings, we cannot combine C and D because the time window constraint does not allow us to do that.
Is there a time that they have to leave the warehouse then?
8 o'clock in the morning.
Oh, okay.
So maybe I glossed over that, but
Oh, no, it is. That's fine. Yeah, okay.
okay, so we will violate the time windows for combining C and D. So what else can we look at? Sorry? E and D. The time windows you think will allow us to do that? Probably not, right? Because both of them end at 12 o'clock, right? E, A, and B. You think something else will not give us better savings than that? Because if you look at E, A, and B, B to A, it's the same route, you're just reversing it. I think we'll get something, I think we'll get a greater savings from doing another combination, because E and B, you'll see that the distance from E to the depot is not very large. So you're not saving a lot over there, right? But you're adding a huge distance from E all the way to A, right? So the savings are not as big as you might get somewhere else. So what is the other place we might get savings from? Exactly, by adding C to the A and B route already. Because remember what we said with the Clark-Wright savings method, you can add stops to existing routes, okay? So let's look at adding C to A and B. So we know that this distance is 10 miles. We know that this distance is 9.2 miles. And from, again, Pythagorean math, we can look at this and we can see that this is 12 miles. Okay? So now, when we consider combining C into the A and B route, our savings is 10 plus 9.2 minus 12, which is 7.2 miles. So let's see where is the tightest time window. The tightest time window, so these time windows are both pretty late. This is the tightest time window, so clearly we want to go here first. So we traverse this leg in 2.5 hours. We get here 10:30, we wait till 11. 11:30, we finish unloading. This is going to take us 3 hours. So we are here at 2:30 in the afternoon. Within the time window, we finish unloading in 3 hours. We finish unloading in half an hour. That takes us to 3 o'clock. This is 2 miles. It takes half an hour. Gets us here at 2:30 in the afternoon within the time window. Finish unloading at 3 o'clock. Within the time window, we can easily leave and get back to our depot. Okay? So we do not. So if we go first, to C, we won't violate any time windows. So, our final solution should look something like this. And now, we cannot combine D into the ABC route, nor can we combine D and E, nor can we combine E to the ABC route. And as a result, we have the solution to our Clark-Wright savings algorithm. So that gives us the final solution. So clearly, the Clark-Wright savings method, or the savings method, is more flexible than the sweep. A small problem with 5 stops took us a long time to solve. in a computer that can take a fraction of a millisecond. In general, it gives you really good solutions. On average, typically about 2% from the optimal, which is really good in a practical setting. So it's a really powerful and very, very widely used method among a lot of the different software that you have for vehicle routing. Okay, so you come up against this issue where you have now multiple routes, but now you only have a limited number of vehicles and a limited number of drivers. Okay? You have more routes than you have drivers. So how do you now manage that situation? So that's where sequencing of routes comes in, and you can have multiple ways of sequencing. Here we're going to make a simple assumption that all we're trying to do is just balance the workload. We're just trying to make sure that all of our drivers, all of our vehicles get the same number of working time, driving hours, on-duty hours as everybody else. So here we have 8 routes, and we have 4 trucks, synonymous with 4 drivers. We have a 9-hour workday starting at 8 o'clock in the morning, going up to 5 o'clock in the evening. And we have to make sure that the routes are sequenced in such a way that we can load them onto each of our trucks, which is really a problem that can be very easily represented as a knapsack problem. So if you think about each truck being a knapsack and each route having a certain weight in terms of the number of hours that is required to execute that route, then we can now see how each route becomes a knapsack with a limited capacity for the number of routes. Each truck becomes a knapsack with a limited number of capacity for the amount of hours that each route can be loaded onto that particular truck. So that's how we formulate this problem as a knapsack problem. And our objective is basically to minimize the number of trucks that we use. So this is a very general way of setting up the problem. We have given to us a number of trucks, which we can call generally n. In our example, we would call n is equal to 4. And we have given to us the number of routes, which we designate over here generally as capital R. In our example, R represents 8, right? Because we have 8 routes. So each route takes a certain time, which is represented to us very generally as T sub R, okay? And the R is just basically the T sub R is the number of hours that it takes to execute a particular route. For example, in our case, you can see route 1 takes 2 hours, route 2 takes 5 hours, route 8 takes 4 hours, and so on. We are given our capacity of the workday. Okay, so in this case, we have an 8-hour workday, and we want to minimize the number of trucks. So we have to specify 2 binary variables. One binary variable is y sub ij, and y sub ij takes on a value of 1 if we load route I on truck j. Okay? And then we have a second set of binary variables, z sub j, and z sub j takes on a value of 1 if we use truck j. So you can see that our objective is very simple. We just take the sum of all the zj values. Remember that we have n number of trucks, so the zj values go from 1 all the way to n. We take the sum of those, and we have to minimize that. That's our objective function. We're trying to minimize the sum of all our zj values. For each truck, we have a constraint. Okay? So our subscript for truck is j. Okay? So for each j, we have a set of constraints where we take the sum product of the time for executing a route multiplied by the binary variable for that route if that route is assigned to that truck. So you can see that in this case we have the time that it takes to execute route 1 times the binary variable if route 1 is loaded onto truck J. And added to that, the time it takes to execute route 2 times the binary variable if route 2 is assigned to truck J. And remember, J takes on values from 1 all the way through n, because there are n number of trucks. Okay? So basically, you're going to have this constraint for each of your n trucks. So you'll have J is equal to 1, 2, 3, 4, 5, 6, 7, all the way through n. Okay? So you'll have n number of constraints. So that's the truck constraint. And then you have a constraint for each route. So now you see the subscripts are switched, where you have the general subscript I going from 1 all the way to n. And now you have, for each route, you take the sum of all of the binary variables for that particular route if it's assigned to truck 1 through n. And only one of those binary variables can take on a value of 1. So the sum of all of those binary variables has to equal 1. Why? Because only one truck can serve that route, right? So you're going to have a constraint like this for each of your routes. Okay? So from route 1 through R, you'll have R constraints for that, for this particular set of constraints. So in this way, you can go in and you can set up all of your formulation, and all you have to do is run the program, the binary program, and it'll give you the solution as to which routes, which trucks are going to be used, how many trucks are there, and which trucks are going to be executing which routes. Okay? Now we can expand upon this, and we can add sequencing indexes. We can add a third subscript, which we say we want to load route I on truck J at a particular RK. And that's how we can now add additional constraints such as time windows to our routes. All right, so that is vehicle routing for us. Any questions? Okay, so we will end today and we will see you on Thursday, but on Thursday we're going to be doing facility location. Okay? So make sure you bring lecture 12 notes to class. Okay? We'll be doing facility location on Thursday.